As we discussed last time, ideally, you should see only the signal at the filter's output, and the filter totally remove the offset. But in a real design, you might still see the residual offset because of the unfiltered ripple. Therefore, if your design specifications are for very low DC offset and flicker noise, you must achieve a very low ripple after the chopping amplifier. But why do you have such a big ripple in the first place? Think about the filtering images for 5 seconds. Bingo! Bad filtering, or in other words, the unchipped analog filter was not good enough to have low cutoff frequencies right on the signal bandwidth. Therefore, you can still see the majority offset could be inside the filter's bandwidth. Especially, we cannot move the chopping frequency high enough. Well, what can we do if we must tolerate such a poor analog filter? Think about a smaller initial offset before chopping for 5 seconds. Correct. If we can magically make the initial offset before chopping is small enough, even though there are some offset inside the filter's bandwidth, the residual offset is going to be small. So, how do we make the magic small initial offset? Right, you know auto zeroing can reduce the offset easily. Therefore, we should do the auto zeroing first and then chop it. Even though we did not improve the low pass filter, you can see both auto zeroing and chopping improves the low frequency noise a lot. But from the frequency image, do you see any constraint of the chopping and auto zeroing in frequency? Bingo! The chopping frequency must be twice of the auto zeroing frequency. As we know, the auto zeroing sampling will cause the noise aliasing folding and increase the DC noise. If the input is chopped at twice of the auto zeroing frequency, the noise is modulated or converted away from the DC to the chopping frequency, or twice auto zeroing frequency, which makes the alias noise notch out at the DC, and the residual offset of auto zeroing is exactly averaged. Besides the complicated auto zeroing added to the chopping, do we have a simpler one to mitigate the low pass filter? Think about the DC block image for 5 seconds. Yes, we could add a capacitor to block the DC offset to remove the ripple. Unfortunately, we need to keep the signal content such that the high pass cutoff frequency must be very low. Therefore, to fit a reasonable area on a chip, we could apply a few picofarad capacitance with the MOSFET transistor in the off region as a voltage control resistor. Is this good? Probably not. If your input signal is too large to keep a good linearity in the transistor, what else could we do? Yes, you can simply apply a duty cycle resistor to achieve a good linearity and low area at the same time. But the duty cycle control must be accurate enough. Do you have a better way of implementing the very low cutoff frequency high-pass filter easily? Think about the integrator images for 5 seconds. Correct. The frequency response of analog integrator is a low-pass filter with a very low cutoff frequency. You must learn this trick in your Microelectronics 101 class in the past to transfer the low pass into a high pass by separating it, which is exactly the negative feedback we are applying here. Since the integrator is not in the main signal path, we can implement the low cutoff frequency easily, and then the residual ripple can be removed by the poor low pass filter. Okay, from this topology, do you have more idea to reduce the ripple? Think about the feedback images one more time for 5 seconds. Bingo! We can sense the ripple and feedback to cancel the input offset. However, the stability of the feedback loop could be a concern because of the feedback path phase shift at the chopping frequency. We like the settling time to be as fast as possible with a high unit gain frequency, which should be well below the chopping frequency to ensure the stability. So we may need to increase the chopping frequency, but the charge injection or clock feed through will worsen the offset. Again, there are lots of trade-offs in the angle design domain. Do we have other simpler topologies to mitigate the chopping ripple? Think about the digital images for 5 seconds. Great. If the on-chip angle filter is not great, why not apply the digital filter? In addition, if our amplifier with offset is used for following ADC, why should we just convert all the angle signal along with the offset and noise into the digital domain? Then, not only the chopping signal is digital, but also the modulation is done in digital. Then, the ripple can be removed perfectly with a digital filter with notches at chopping frequency. Of course, the ADC would have lots of design challenges with lots of calibration needed here. Again, there are lots of topologies in the chopping amplifier, and please let me know if you have other questions or ideas. Here are the summarized images of why we need a low ripple after chopping the amplifier for very low DC offset and flicker noise. Since the on-chip angle filter was not good enough to have a low cutoff frequencies right on the signal bandwidth, the modulated offset could be inside the filter's bandwidth, and then the residual noise is still high. So the first image is that we can apply the auto zeroing we learned first to make the initial offset before chopping is small enough. Then the residual noise would be still low enough. Second, we could apply an AC coupling high-pass filter in the signal path to remove or block the DC offset easily, but we push the difficulty into a very low cutoff frequency high-pass filter in the signal path. Instead of doing that, we can try the third one through an angle integrator outside the signal path with a very low cutoff frequency. Fourth, the negative feedback idea can be applied here to sense the ripple and feedback to cancel the input offset. However, there are trade-offs between the stability, settling time, chopping frequency, charge injection, over clock feed-through, etc. The last one is digital filtering by putting the demodulation and filtering after the ADC, which may require lots of calibration to mitigate the ADC's impairments. Again, the digital filter should have a good notch and chopping frequency to filter all the ripple pretty well. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.